signal. For non-deterministic signal or a random process, you take the expected value inside. So basically, this is x of t. You take expected value of x of t of x square of t, and then you integrate from minus t to t, and then you divide, of course, by 1 over 2t, and then you observe for very long time, or long enough time, as we mentioned last time. This is what t goes to infinity means. Okay? This is in time domain. So this is the way we do it in time domain. Now, if I want to calculate the power, اللي هو نسميها pxx here, as in the frequency domain. So what do? I take x of t, one realization, for example, and I take the Fourier transform for that. The Fourier transform will be something like this is omega. I will call it x t of omega. So basically, I'm talking here about from minus t to t. I take it x t of omega, which is the Fourier transform of x of t xt of t, where xt of t is defined from minus t to t. Okay? So basically, I'm looking at a signal from minus t to t. I take its Fourier transform, I get x omega of omega. I don't know. It's something like this. Okay? So basically, this is what I get. Now, I take the expected value of this, because this is only the x sub t of omega is the Fourier transform of one realization. One sample function. So in order to take it for the whole random process, I need to take the expected value of this Fourier transform. Okay? And I divide over 2t, and I take t to infinity, which is, again, observe for long enough time. Okay? So simply, I'm talking about looking at this function, اللي هو in red. This function in red is called the power spectral density. What does this mean? لاحظوا هنا what I'm trying to do. In order to find the average power, I am integrating this over omega. I am taking the area under the curve. Right? What does this give me this as? تذكر ال PDF, when I integrate the PDF, when I integrate it over all the values of x, what do I get? I get over the total value of the probability, which is 1, right? So if I integrate this function over the whole range of omega frequencies, all the frequencies, I get the average power. So what does this function mean? It's a density function. It's the power spectral density. It gives me how is average power of x of t distributed over different frequencies. مثل ال PDF gives me how is this total probability of 1 distributed among different frequencies. Here, the power spectral density gives me how is this average power distributed over different frequencies. At this frequency, omega 0, do I have large amount of power or a small amount of power? If I want to filter, which cutoff frequency I need to use, depending on how spread this power spectral density is. Okay? And this is a very important concept, because this will allow us later to be able to filter and process random processes according to their perceived power spectral density and the cutoff frequency and so on. So the average power here is the integration over all frequencies is the sum, the area under the curve of power spectral density, yes, PSD. Power spectral density is PSD. Power spectral density, PSD. We will use it all over the two chapters, the next two chapters. أي سؤال يا شباب؟ So if you look at the average power is related to the time average of the second moment. زي ما تكلمنا ذيك المرة. هذا time average. A is the time average لو تتذكروا من last class. Time average. It's the time average of the expected value of x squared. لو تتذكروا دائما أنا كنت أقول لكم إنه كنا نتكلم عن المومنتس. We will later establish or connect the second moment of a random process to the power for the White sense station. أي سؤال يا شباب؟ This is a very important concept here, and we will build on it as we move today and next class, the next two classes. Any question? So let's have an example. We have here the random process is given by or defined as A0 cosine omega 0 t plus theta, where theta here is the random variable, which is the U means uniform. Uniform between uniform over من كم لكم 0 to 2 pi. Sorry, pi over 2 as given here. Okay, شباب. So basically you have a random process which is whose phase is random. هذا تكلمنا عنها قبل كده. This is a typical phase modulated signal, right? Where the random signal is carried over the phase. Now I would like to investigate this power. Let's see. Expected value of x squared. هذه هي الباور. If I take the average of that, if I take the time average of that, I get the average power. So I start in order to get the time average of, the average power, I simply need to find first the expected value of x squared, which is equal to, if it is White sense stationary, this is equal to Rxx of 0. If it is White sense stationary, if White sense stationary. If it's not, then it is not. Okay, so basically the expectation as usual, what do I do? In order to find this expectation, I take whatever inside, I just replace it with its value. So x squared is a squared cosine squared inside the expectation. But cosine squared is 1 plus or half, 1 half plus half cosine double the angle. Okay? Now if I take the expected value of the first part, what do I get? Expected value of A0 squared over 2. What is this equal to?
A0 squared over 2.
Yeah, it's constant because of that it comes as it is. It's constant. And the second one, expected value of A squared cosine 2 gamma 0 t plus 2 theta. Now we know that here theta is not defined over 0 to 2 pi, so we cannot say it's 0. It's defined over only quarter the period, 0 to pi over 2. And because of that, we need to do this integration. It's the integral of the cosine, and this is the PDF. This is f theta of theta. It's 2 over pi, so that we guarantee that. So basically, f theta of theta is up to pi over 2, not 2 pi. and it's 2 over pi, so that we guarantee that the area under the curve is 1. And if you do the integral and calculate it, this is equal. This is what we get. It's expected value of x squared of t. And it's a function of t. Because of that, this is not White's station, because it's a function of t. It's not a function of, it's not a constant. If it is White's stationary, then this is a constant. So now, in order to find the average power, we need to take the time average. Time average of expected value of x squared. The time average is whatever inside. The time average is an operator, as we did before. Whatever inside, we take it inside the time average. So we integrate from minus t to t of expected value of x squared and divide by 1 over 2t and take the limit. And if you do this, you will get it's a squared over 2. واضحة يا شباب؟ How did we do this? Do the integral. Do the integral. Okay, do the integral so that you learn how to do the time average. Alternatively, we could have taken x of t and find its Fourier transform. And then take the Fourier transform amplitude square, which is multiplied by its conjugate. And then the average power will be this power spectral density, which is the expected value of whatever we will do here. It's the expected value of it divided by over 2, divided by 2t, and then you integrate, you take the Fourier transform of that. Oh, sorry, you integrate over omega. So here xt of omega is the Fourier transform of x of t. So you need to take the Fourier transform of this, take 2 deltas, take the magnitude square, and then integrate over the frequencies. You will get the same answer. Same answer. Check it yourself, try it yourself. As you can see, this is all 207 now. But you need to understand, to connect the concepts of 315 with what you learned in 207. Any question? Shabab?
No.
Everything is clear to all? طيب.
Doctor,
تفضل.
does that mean the average value will not depend on the random variables theta?
The
Or it
average
should be
power?
that?
The average power?
Yes.
No, it should not. The average power should not. Expected value of x squared هذه is a function of time. هذه تطلع وتنزل تطلع وتنزل. لكن ال average power of the signal is the time average of the expected value of x squared. انت اذا عندك سيجنال مركبها just تشوف على الاسوسكوب او سيجنال جالسه مثلا coming to the mobile, or basically looking at a random signal that is basically coming from a generator. At the end, the average power is the long-term average, time average of whatever randomness. So this average power has to be constant. Whether it's stationary, White's stationary or not White's stationary, because you are taking the average power. You are observing over a very long time. واضحة؟
Yes, doctor.
طيب الآن إيش علاقة الأوتو correlation function بالpower spectral density? It's very simple. If it is White's stationary, the auto correlation function and the power spectral density are Fourier transform pairs. So the auto correlation function, I take the auto correlation function, Fourier transform of that, I get the power spectral density. Now, if it is not Whiteson stationary, if it is not Whiteson stationary, معناها إيش؟ معناها Rxx of t and t plus tau does not depends on t, not only tau. So in this case, I need first to take the time average of autocorrelation function. واضحة؟ I know the autocorrelation function changes with time. نقول changes with time. Changes over time. So in this case, I need to take the time average of this autocorrelation function. I take the Fourier transform of that. I get the power spectral density. So the power spectral density is the Fourier transform of the time average of the autocorrelation function. واضحة شباب؟ I take the Fourier transform of the average autocorrelation function. طبعا for Whiteson stationary زي ما قلنا time average equals the autocorrelation function. لأنه أصلا the autocorrelation function doesn't depend on time. So time averaging a function that doesn't depend on time يعطيك نفس الفانكشن. And because of that, the autocorrelation function is the Fourier transform of Sxx of omega. It's the inverse Fourier transform, and the power spectral density is the Fourier transform of the autocorrelation function. This is for Whiteson stationary. For non-Whiteson stationary, the same applies, but here this will be the average, the time average of the autocorrelation function. Okay, if not Whiteson stationary. واضحة يا شباب؟ هذه العلاقة بين autocorrelation function والspectral density. Any question? طيب, let's have an example. So here we have autocorrelation function is given by this. Okay, so basically you can see that it's clearly an autocorrelation function that هذه here plotted here. It's a cosine wave. It's a periodic cosine wave. So you can see that this is a Whiteson stationary, right? So the autocorrelation, sorry, the power spectral density is the Fourier transform of the autocorrelation function. If I have a cosine wave, what is the Fourier transform of a cosine wave?
2 shifted delta.
2 deltas, right? With the amplitude divided by 2, and we have pi here because of the equation of the Fourier transform we are using. So basically we have here 2 deltas at plus and minus the omega 0. So what is the frequency component here? What is the frequency component of x of t? You can, how to describe x of t? It's a single tone, right? It has a single frequency component, which is omega 0. So if I want to filter this signal, I need a low-pass filter that at least includes omega 0. So the importance of this chapter is to understand how to filter, how to process random processes by understanding the frequency contents of these random processes. Which frequencies are included with which amount of powers, so that if I filter the random process, I know how will I get, what will I get at the output of the filter. Will I lose a lot of frequencies? Will I go to everything out through the filter, What? Exactly. So we need to understand the spectral characteristics of a random process. اوكي؟ لو تتذكروا هذه كانت السيجنال كانت something like this. A cosine 2 pi A cosine omega 0 t plus theta. كان هذا random variable لو تتذكروا. سوري الثيتا كانت random variable. I'm sorry. ثيتا كانت random variable 0 to 2 pi لو تتذكروا من chapter 6. Example. One of the examples. So when we calculated the autocorrelation function, we got this function. واضح إنه الكوساين ويف هذه المين frequency is, although it's random because the theta changes, however the main frequency is omega 0. And because of that, when we calculated the power spectral density, we got what? A single tone, which is at omega 0 and minus omega 0. هذه نسميها spectral density because it gives you how is this average power. لو تحسب average power Pxx هتلاقيه كم equal to كم pi A0 square. Okay, so basically when you calculate the average power, you will find that this is the density of that. Any question, شباب؟ طيب, another example is the autocorrelation function is given by this triangular function, which is mathematically written as from minus t to t by this function. It's a triangular اللي شايفينه قدامكم. So basically the autocorrelation function simply is maximum at A0 and then dies off up to t plus t. So basically the signal after t seconds becomes uncorrelated with itself. مثلا هنا after t seconds السيجنال ما لها علاقة بالثانية. يعني مثلا الآن if I plot the curves هذه اللي sample functions and I compare the signal now at t0 and after t seconds t0 plus t seconds, the signal now and after more than t seconds, the correlation between them is what? Is zero, uncorrelated. ما لهم علاقة ببعض. So the signal at t0 and after more than t seconds, capital T seconds, become uncorrelated. ما لهم علاقة ببعض. So this is what this shows. X of t and becomes, sorry, uncorrelated with x of t plus capital T and above and more. Becomes uncorrelated. ما له علاقة ببعض. Now if I take the Fourier transform of the autocorrelation function and I calculate it, I get basically sinc square, which looks like this. لو تلاحظ السينك square has inverse relationship with t. So as t increases here, إذا t كبرت معناها ال autocorrelation function becomes wider. So if I compare large t with small t, large t means basically it looks like this. هذه t وهذه minus t. هذا ال autocorrelation function. Small t, it's another autocorrelation function. Narrow. So this is t minus t. Rxx. So I'm comparing two signals here. واحدة large t, واحدة small t. Now if I take the Fourier transform of this, I get the sinc square, right? With narrow. Because this, the first lobe here is 2 pi over t. So if I have large t, I have small bandwidth. So this is sxx of omega. بينما هنا, if I take the Fourier transform, what do I get يا شباب? I get a large 2 pi over 3. So the bandwidth of this, small bandwidth, right? While here it has a large bandwidth. ايش يعني؟ ليش يا شباب؟ نعم؟
علاقة عكسية.
علاقة عكسية أيوة. ليش؟ لأنه هنا T is very large, so the signal stays, it changes very slowly. شباب جهزوا كاميراتكم، ترى قربنا. جهزوا كاميراتكم الله يخليك. T here is very large, which means that the signal moves very slowly. So the signal, and after capital T, which is large, يا دوب تصير uncorrelated. قبل كذا correlated. And because of that, if I take the Fourier transform of that, I get the power spectral density, which has a small bandwidth. خلينا نقول null bandwidth. بينما هنا it changes very fast لأنه capital T is very small. يعني ممكن هنا 1 millisecond. After 1 millisecond, the signal becomes uncorrelated. خلاص تتغير تماما. بينما هنا ممكن after 1 second, the first, large T. And because it changes very fast, the power spectral density is very wide, and hence it has a large bandwidth. So next time, inshallah, we'll continue the discussion. This is very important, Shabab, so that you understand the relationship between the autocorrelation function and the power spectral density.